All right, thank you to everybody who has stuck out to the end, or almost the end. Um, this is a extended talk that Jen Helbin gave for me at the IRSRU workshop last week. I wasn't able to attend for some medical reasons. So some of you have seen some of this before, but hopefully there's some new enough stuff that, okay, let's go forward, that you won't be too bored. So one of the reasons I started this work was as part of rover projects that I've been trying to work on or trying to get going. We need to really understand what we needed to do when we got to the surface of the moon. And it's when you start to drive level 2 requirements and the systems engineers start asking you, well, why do you really need to drive that much? You know, you need to have actually a real rationale rather than because we gotta, you know, we gotta find the water. So I really started over the last year or two developing ideas about really how to quantify what we need to do to actually characterize resources, water in particular, in ways that are meaningful to the resource community and the mining community here on Earth. So I really borrowed a lot of the techniques and methodologies from what folks at the USGS or mining companies would do. In particular, you start to look at the geostatistics, start to use some of the same methods of interpolation, extrapolation, et cetera. And then in this talk, I actually show how it's applied to a field test we did back in 2014 in the Mojave Desert. And we have this data set from that can really help us actually validate from real data, not just simulations, some of these techniques. So what we're trying to do is understand what it is we need, the data we need to take to build a mineral model. A mineral model is something you use to go from some other data set to understanding and estimating the total reserves of a resource, for example. To do that, what I've done is I've built a number of Monte Carlo simulations that look at random variations, distributions of water, concentrations and depth, and actually also included instrument models that include how they measure the water, or hydrogen in this case, and instrument noise, et cetera. Use those to understand the truth. How well can we estimate these things, and then use some of these geostatistics to understand our uncertainties in that. And then I'll show how that's done with some field data. So one of the first things I looked at was, because when the engineers say, well, how far do you need to drive? They say, you know, they want to go 10 meters and be happy. It's like, no, we might need to do better than that. A possible determinant of spatial scale can be done with using variograms. Variograms are just a means to actually look at the correlation of any particular data with some kind of distance or lag, distance between points. What I'm showing here are several variograms. Basically, the variance is a function of lag, or distance from the origin, where you started the measurement, for depth to stable ice data. So this is 20-meter depths to stable ice modeling that Matt Siegler and Dave Page provided to us. And what it shows basically is where the autocorrelation ends, which is called the sill, where you kind of roll over here. At that point, the range indicates a change in the, basically in the spatial scales at which things are varying. And when you look at this, the bottom line is, the takeaway is you see these various points where this data rolls over, continues, rolls over, continues. Those various ranges are giving you estimates for the degrees at which the phenomenology is changing. You need to measure across these distances, or you could be having aliasing problems, missing fundamental scales, et cetera. Just using this data, which is for an area near the North Pole, it told us we needed to really rove hundreds of meters to kilometers, you know. But at the same time, you need to measure things down in the 10 meters. You can't just hop 1,000 meters and call it a day. There's a range of scales. Not surprising, but it's important to really actually put it in quantitative numbers for a mission. So understanding that, that's the first problem we need to understand, how far we need to go. Well, how are we going to go about prospecting and identifying the water? We've been developing this technique. It's not a new technique. Others have thought of this before too, but I really like it. It's using basically a neutron spectrometer as a continuous monitoring source while you're roving. And the reason for that is, just like here on Earth, drilling is expensive. And people don't go out, even when they're on Earth and they want to understand a resource, they don't drill hundreds and hundreds of times. They drill 20, 30, 100 times, and will use that data along with other data to develop a mine. Neutron spectroscopy is nice because you can sense down the subsurface, you can sense very small concentrations of hydration, and you can do it continuously while driving. Basically, drilling, if you will, every single meter, or whatever the footprint is of your instrument field of view. Now, there is an issue with that, in that there is some ambiguity to it because of the relationship between the neutron energy flux and the concentration versus burial. And this figure, which Rick Elphix provided to me, I call this a spider chart. It shows the thermal and epithermal neutrons versus the epithermal neutron counts for a range of water concentration, that's the orange lines, and various burial depths. So the thickness of the dry layer above it are the blue lines. And you can see, for any particular count of epithermal, thermal, and thermal, you can get the same count for a range of burial depths and ice concentrations. So every once in a while, you do need to drill and basically tie down where you are in this spider chart, but you don't need to do it all the time. You can just do it in several distinct places. And you can do that with a borehole and combine near-IR or some other sample analysis that tells you at what point, at what depth, the water ice that the neutron is sensing. These are examples from the Mojave field test we did with near-infrared reflectance while driving and neutron flux while driving, and I'll show this a little bit more later. So this is the kind of model I started with when developing these Monte Carlo simulations for a mission to identify, characterize a region. What we've done is we basically generated random simulations of mixtures of water. This is X by Y. This just shows high and low concentrations of water. The green means higher concentrations of water. And I've got a model for the burial depth that, in this particular case, is a function of the concentration of water. So running along this line, the burial depth looks like this. We can take this, the mean concentration per cc, the burial depth, and get a total column integrated mass. And that's what, for example, if you're mining, you might be interested in from an economic standpoint. What I've drawn on top of this is a traverse. It's just an example traverse that I actually run a neutron spectrometer across, and using a neutron spectrometer model, calculate the neutron fluxes, and from that estimate the total water along that traverse. So that's what this is here. I used the predicted water along the traverse to predict what the water is along this traverse, only that traverse, and that includes the instrument noise and the uncertainty in burial depth, et cetera, et cetera. But from just that data, I can use a number of various Gaussian regression techniques. This particular case I use Kriging, to interpolate across this entire area. And that's what shows here. So this predicted water mass map is generated only from data along this traverse. And if you squint, I'm actually quite impressed that it does that well. And this shows the difference between the actual and predicted water. And not surprisingly, where you are getting further away from your traverse, you're going to have higher and higher uncertainties or errors in the prediction. I did this a number of different times with basically smaller or larger traverses, including, for example, just single points, like a single static lander measuring one place, and ran this model hundreds of times and created basically an estimate of what the 1 sigma uncertainty in the predicted water for this area would be as a function of the percent area covered with your traverse, or another way to look at a number of unique 2 meter by 2 meter samples. And you can see it's a strong function as a function of percent area. And when you get down here, for example, this blue shaded area is something you might expect if you landed 10 static landers in this 33 by 33 meter area. For this particular water distribution I'm modeling, which is consistent with something you might expect from impact gardening. So it really tells you that you cannot accurately, from a resource standpoint, model or predict what the resources might be using just static landers. You need mobility, especially if there's scales and variations as small as of tens of meters to hundreds of meters. But it also tells you that you don't have to paint the entire area. If you get a 10 to 15 to 20% coverage, you're actually getting that water concentration quite well. And you can actually then develop sampling strategies this way. Others have done this so that you can beat this air down further and further and further. So a quick example of using more of this geostatistical interpolation, the Gaussian interpolation technique, I turned to some data we took out in the Mojave. It was across this beautiful alluvion fan with desert pavements across it. That's these darker regions. What we did is we had a rover mounted with the neutron spectrometer system and the near-infrared spectrometer system, and we made various traverses of various sizes to actually study what we needed to do to characterize the water in this area. The water concentration in this area is around 3 to 10%, so not unlike the moon. Here's an example of an overlay down on one of these aprons here of the alluvial fan. The darker areas are pavement. Pavement is basically stones overlaying the surface. This shows neutron counts, with red being low neutron counts and blue being high neutron counts, meaning more hydration. And we can use just these kind of traverses here. We have a high density traverse versus low density traverses to really understand the kind of coverage we need to do to predict the water. And this shows, just using those traverses, a prediction for the entire area, showing the hydration within this desert pavement. And we've then dug in places, and with a near-infrared spectrometer, we're able to understand the distribution of the water vertically. So combining those, that's the next step, we can actually make predictions of the total hydration in the Mojave and its association and distribution with these pavements. What's nice about that is then you can take another data product like albedo and extrapolate it to much greater areas. And that's it. Summary. Thanks. And it's a beautiful chime at the end. I didn't know that.
Okay, questions?
Buzzer. Hi, Paul.
We do have drill holes. There's about 10,000 craters in the last 5 million years, bigger than 30 meters. About yours is one of them.
Yeah.
We ought to probably take advantage of those natural drill holes.
Yeah, absolutely. And there's a new paper out that kind of looks at that, right? The depth of diameter in association with water. Exactly how to do that, I'm not sure, but yeah, if we can do that, that'd be great.
Yeah, the point is to measure the water content in the ejector blankets at the surface, like you see on Mars. Polar regions on Mars, little impactors show icy ejector blankets.
Right, right. And whether or not we can see them in the ejecta blankets on the moon is the question, right? Yep. No, and your point's a good one too. That's actually a process I'm very interested in, is understanding that redistribution with that impact event, natural impact event. And if you went to a relatively fresh crater that was 5 meters deep, is it going to really show you something excavated from 5 meters down from a water standpoint? Definitely something we should look at.
No more questions?
All right, thanks.
Thank you.